Okay, we want to learn what the effect of a concentrated moment is on the shear and bending moment diagrams. So we're going to start with this particular beam with a concentrated 20 kilonewton per meter moment at the center. And first I just like to, well, you know, what you can think of it is that, well, that we have this concentrated moment, and if we were to apply this to this beam, I think conceptually we can all agree that the deformation of this beam would be something like this, S-shaped. That's all we're applying, and it's a very simple deformation. In other words, the beam is basically going up in this region, it's going down in that region, and we get that S shape. Understanding that that's the deformation is important to us, and we'll see why a little bit later. First thing I'm going to do is just make sure we can all get the reactions, and we're going to draw the shear and bending moment diagrams. And I want to note one other thing, and that is when we draw a roller in this manner here, where I just draw this little circle on the bottom, that is a conceptual, not a conceptual, it's just a little schematic that is not necessarily accurate. You should think of the roller, if we're going to make it in more detail, is going to look something more like this. And in other words, I really have a roller at the top and the bottom. I'm not, in other words, I'm constraining vertical movement, but not horizontal movement. So so we just keep it simple. Everybody draws it like this, but there's more to it than that. In other words, we get constraints from both the top and the bottom. All right, so to get the reactions, here's my free body diagram. AY and BY are shown. I take moments about A, and what do I have? I have minus 20 for that, and minus BY times 10 for that. I solve for BY, I get negative 2 kilonewtons, and then I take moments about B, and what do I get? I take moments about B, I still get the minus 20 for that, and plus AY times 10 for that. So I solve for AY, and I get 2 kilonewtons. Now what does that mean? That means I get AY is upward 2 kilonewtons and BY is downward 2 kilonewtons. And if I look at this, what do I see? I see what goes up, which is 2, what goes down is 2. It's an equilibrium. And so that ends up being correct. Now, I'll start by making some cuts again to show the influence of this concentrated moment. So I'll make a cut there to begin with, and I'm going to make a cut over here. So let's just take a look at those two situations. So that cut there is this free body diagram here. I have my V, N, and M, as I always have, and the way that I said was positive. And I take the sum of the forces in the y direction equals 0, and I get V equals 2 for that. And I take the sum of the moments about, I'm calling this point C. That is point C here. And taking moments about point C, I get that M is 4 kilonewton meters. And okay. So at a distance of 2 meters, so we made a cut at 2 meters here, and we get M is 4 kilonewton meters, we get V equals 2. All right, so we're going to make a cut at X equals over here, which is 7 meters. So I'm going to take this free body diagram, and that is represented over here. Now, in that free body diagram, because in my 7 meters, I still have my 20 kilonewtons. So I have to put that into my free body diagram, and that's going to change things a little bit. But if I take the sum of the forces in the y direction equals 0, on this free body diagram, I still get V equals 2, because obviously this 20 kilonewton meters does not influence the forces in the y direction. However, when I take the sum of the moments about D, and this is this point D is over here, then I have a different equation. So I have the 2 times 7 for the AY, I have the minus 20 for that, and then I have minus m. So I solve for m, I get negative 6 kilonewton meters. So at 7 meters, I get minus 6. At 2 meters, I get 4 for the moment. But notice that at 2 meters, I get V equals 2. At 7 meters, I get V equals 2. So my V hasn't changed. So if I look at this, I'm going to find, well, that it doesn't matter where I make my cut. I'm going to make my cut at any of these places here. I'm going to end up with V equals 2. You can try it yourself, make more cuts, and that's what you're going to find. So now what's going to change? For instance, what would change if I made a cut at 3 meters instead of 2? Well, if I look here, that would be 2 times 3, not 2 times 2, and I would get m equals 6. If I made a cut at 4 meters, I would get 2 times 4, I'd get m equals 8. So, and then once I go past, if I go over here, so if I make a cut at 6, this would be 2 times 6 minus 20. So that would be negative 8. And if it were at 9 meters, for instance, this would be 2 times 9 minus 20, which would be negative 2. So we could do this, almost in our head to get these answers, and what we would find is that we would get a free body diagram. Well, there's our free body diagram there. And what would we get? Like I said, no matter what, we're going to get V equals 2. So I get my shear diagram would be V equals 2 everywhere. And then what we would find for the moment diagram is the moment diagram would look like this, just using the reasoning that I just came up with. We would get those points, depending on where we make a cut, and then you should do the cuts yourself. But we would get a moment diagram that would look like this, look like that. Okay. So I'm going to make some little generalizations here that we can do and come up with a shortcut method because it's, too problematic to do all these cuts. So let's start with the shear diagram. And what do we see? Well, we've said follow the arrows. So what do? I follow the arrows here. There they are. I go up to, over, down to the end. And what does that mean? I ignore that this has no effect on my shear diagram. So the rule for the shear diagram is, the concentrated moment has no effect. Okay? Has no effect. Now, what we're going to find out is, though, but divide up the area at that location. So we have to do the areas, and what we're going to do is I have this concentrated moment here, so I'm going to divide up the area right there, and we'll see why. So that I have an area 1 and area 2, and if I do this, I'm I have area 1 is 10 kilonewton meters and area 2 is 10 kilonewton meters. So now when we do the moment diagram, what do we see? Well, we had all the points, so we draw a straight line there, and then we draw a straight line there, and we have to connect it with a vertical line. Now let's take a look at, let's see what we get here. So area 1 is 10 kilonewton meters. So I can use my method. I start at 0, and what do? I go up to 10 kilonewton meters there, going from left to right with the area. And then notice what happens. This is 20 kilonewton meters, and this drop is 20 kilonewton meters. So I drop there, and then again, this area is 10 kilonewton meters, positive. So I go like that. So what do we learn? This is about the shortcut method, is that for the moment diagram, a counterclockwise concentrated moment means jump down. So in other words, this is a counterclockwise concentrated moment. That means I draw my moment diagram, and oh, it's counterclockwise 20, I drop 20. And then continue with the areas. So we're going to find that if we have a clockwise concentrated moment, it means jump up. So these are two more rules for the shortcut method that you need to know, those rules. All right, let's try this. And so I have a concentrated moment there, I have a concentrated moment there, and there's my beam. I'm not going to go through the reactions. You can pause the video and see the reactions here. So I get my AY is 0.333 upward, my BY is 0.333 kilonewtons downward. And what does that mean for my shear diagram? Well, it means my shear diagram is start at 0, I follow that area up 0.333 and I go down 0.333, I end up back at 0. Our other rule, though, said that everywhere we have a concentrated moment, we need to break up our areas to help us solve this problem. So I'm going to break up the area. I've got area 1, I've got area 2, I've got area 3, all rectangles. You can all figure out those areas there. And now we do the moment diagram. So I go up area 1, but now here's the thing. When you have concentrated moments, you can't do just the areas. In other words, remember our rule was we do the arrows and then we do the areas. Well, now we're adjusting it a little bit. When we have concentrated moments, we have to pay attention. We can't just use the areas. We have to account for the concentrated moments. So we have our areas. There they are. But now we look for concentrated moments. So we have to look at them. Do we have any concentrated moments? Oh, yes, we do. So I'm following the area. Area 1. This is counterclockwise. That means I drop down 8. Now I do area 2. Go up. Oh, I have a concentrated moment. That's clockwise. So I now go up 5. And then area 3 takes me back to 0. So the shortcut method works very well. You just have to pay attention to those concentrated moments for the moment diagram. And yeah, and then of course the concentrated moments, of course, they influence the reactions. So they do influence the shear diagram by changing the reactions. But when we once we have the reactions, when we draw the shear diagram, we don't really pay attention to those concentrated moments, except that it helps us break up these areas. Okay, let's try. Yes. Try another one. I'm going to let you do this one. So I have calculated the reactions for you. You can look at the reactions here. And but what I want you to do is I want you to pause the video and do this problem. Okay, I'm going to assume that you've done that. So what do we do? We start with a shear diagram. I go up 3.75 over, down 8, over, I ignore that concentrated moment, up 4.25, takes me back to 0. There's nothing there, so I'm like that. I need to break up the areas at this one and this one. There's no area to break up over there, but I break up the areas then. And I have area 1, area 2, area 3. You can all figure those out. So now the way you look at the moment diagram is I have to use the areas, but I also have to pay attention to the concentrated moment. So I go up area 1, I go down area 2, but then I hit this concentrated moment. It's counterclockwise. I drop. Area 3 is negative, so I go down. I go straight across, and then I hit this is a concentrated moment clockwise. That means I jump up, I end up at 0. So I start at 0 and end at 0 as I should. That is the... Now, how do we get these concentrated moments? I want to introduce this. And with the double-handled wrench. This concept here, in a sense. Suppose I have a bolt here on the beam, and then I have a wrench there, and I'm going to twist the bolt. Well, I'm going to apply an upward load there, downward load there on the wrench, and I think you all would agree then that we would get, again, we would get this S-shaped beam because I'm rotating this. Ultimately, I'm rotating this counterclockwise. So now what is the magnitude of that counterclockwise rotation? Well, I've got, here's my bolt. I've got 3 kips times 2 feet, 3 kips times 2 feet. So it's 3 times 2 plus 3 times 2. 6 plus 6, 12. So I have 12 kip feet. And so what I want to do is I want to, I don't want to have this wrench on my beam. I'm analyzing the beam, not the wrench. So instead of showing the wrench, what I want to do is I want to show the concentrated moment caused by that wrench, the twisting of that wrench. So twisting the bolt with the wrench is a better way. So I put in my 12 kip feet like that. And now I have this free body diagram. I can use this free body diagram to come up with my reactions. I get these reactions here. Once I have that, then we've done this problem before. I go up 0.923 over down, get my areas, area 1, area 2, and it's going to, you can do this problem with the numbers. I'm not going to do this. Well, when I say I'm not going to do it, here is the answer. You should do it and pause the video and done it. It takes just a couple seconds, and so I get area 1, I get area 2, go up area 1, then what? It's counterclockwise. I drop down. We've done this one, so go ahead and take a look at it. Okay, what about a single-handled wrench now? So this is just a single handle. Well, now that puts a little bit of a change into it. I've got my bolt here, and now what do I have? Now I just have 3 times 2, 6. I don't have the balancing upward force on the other side. So what does that mean? Well, when I look at, let's think it through for the deformation of the beam. Well, what am I doing here? Because I am putting this downward force that is not balanced by an upward force on the other side. If there were, if there was more to the wrench there, because there's no upward force, what happens to this bolt? Well, that bolt is going to go downward. So I'm going to get a shape that looks a little bit more like that. I'm not going to. But so in other words, I get this point translated downward. I still sort of get this S shape. Yeah. So I don't want to. I could take free body diagrams of the wrench and of the beam, and when I've done that in the past, it ends up just confusing students. So I'd prefer that you just do this based on a certain intuition that I'm describing this. But if you want, please go ahead and take free body diagrams of the wrench and then apply that to the beam. But you will see that that this 3 kips, it acts downward through the bolt. I should get 3 kips there to keep this wrench in equilibrium. So I have 3 kips there, and then I have my counterclockwise 6 kip feet. So when I remove a single-handled wrench, so I have to remove this to do my shear and bending moment diagrams, because again, I'm not analyzing the wrench, I'm analyzing the beam. So I remove the wrench from my free body diagram, and you have to make sure that you understand that this 3 kips gets translated through the bolt to the beam. It doesn't go out here. Some students want to put this 3 kips out here. There's nothing there. It doesn't go over there because there's nothing there. There's no way that 3 kips gets translated to the beam at that location. It gets transferred, is a better word, to the beam through the bolt right there. So there is what I want to put on for my single-handled wrench. So note the 3 kips acts at the bolt. Note that. You need to know that. Okay, so once I have this, I can find my reactions. You can pause the video. Oops. You can pause the video and see the reactions here. And so I get 2.077, 0.923, and that means that I go up, over, down, over. I get my areas. Those are my A1s and A2s. I do my moment diagram. I go up area 1. I have to remember I have a concentrated moment, 6 counterclockwise, so I drop 6, and then that's a negative area, so I go down like that. So I'll put it this way. Notice that if I compare these two, so I have my shear and bending moment diagram looks like this for my single-handled wrench. For my double-handled wrench, was completely different. So just be aware that you need to pay attention to single-handled wrench, double-handled wrench. All right, I want you to do this problem. So pause the video, single-handled wrench here, 9 kips there. So you want to, I've given you the reactions, but you need to do the shear and bending moment diagrams. Okay, I'm assuming you pause the video. What do I do? How do I do this? Well, single-handled wrench, it's 5 times 3 is 15, and that's going to be clockwise. You can see that that's obviously a clockwise rotation that we're putting there. And then the 5 kips gets translated to the bolt. That's where. And then I have the 9 kips here. So we have this free body diagram. And if you want to see how the reactions are obtained, you can read this. So you should be able to do that. I now have this final free body diagram where I have my reactions there. So what do? So I start at 0. I'm following the arrows. Down 5 for that, over. Up 10.5, over. Down 9, over. Up 3.5, back to 0. So there's my shear diagram. Now what do I need to do? I need to draw the moment diagram, and remember, I use the areas, which we can get, there they are, but I have concentrated moments, so don't forget the concentrated moment. So here's what I've got to do. I start at 0, but what do I see? There's a concentrated moment immediately, right at the very beginning here. What do I have to do? I have to jump. I have to jump up because it's clockwise, 15. So don't forget to make that jump, all right? And then I go down area 1, I go up area 2, go down area 3, end up like that. Now, what you don't want to do, and this is what you have to remember, you've got that concentrated moment right there, and you have to catch it right at the very beginning and jump upward. What students will do is that they'll not do that jump, and they'll go down here like this, up like this, down like this, and they get done, oh, I'm not at 0 anymore, and they just draw a line upward. Don't do that. If you're not at 0 at the end, you don't just arbitrarily just start making jumps back to 0. So don't do that. You have to, something's wrong if you end up not at 0 at the very end. And then if something's wrong, redo it. You got to redo it. All right, I will stop there.